Elasticity of substitution. So, in a sense, it means how easy it is to substitute one input for the another, right? So, along an isoquant, how easy it is to substitute one input for the another. There are many things related to it. So, let me just start writing it out. You will understand how easy it is to substitute one input for another, right? So it measures how easy it is to substitute, or it is to move along the points, right, between the different points along an isoquant. How easy it is to move, or how easy it is to move, right, between points along an isoquant. Along an isoquant. So you mean this, beta? So you have an isoquant like this, and you have labor, you have capital. Mhm. And let's say you're sitting at point A, and here you are sitting at point B. And beta, this is going to give you the amount of labor and capital input which you are going to use now. So this is telling you this is the amount of labor input, this is the amount of capital input at point A. This is telling you this is the amount of labor input, this is the amount of capital input at point B. This is what it is, right? So you have labor input, capital input, labor input, capital input, right? And you can also measure MRTS at these points. Tuk, tuk, tuk. है ना? You can also measure MRTS at these points. So MRTS is the slope of the isoquant at these points. Slope of the isoquant at point A and at point B, right? So when you move along an isoquant, right? So when you move along an isoquant from point A to point B, what happens is that your K by L ratio is also changing and MRTS is also changing, right? So how do you do this? That is in moving from point A to point B on Q is equal to Q naught. That is your Q naught isoquant, let's say, right? Q is equal to Q naught isoquant. Both K by L is changing. So here K by L ratio is this, K1 by L1. Here K by L ratio is this, K by L ratio is this, K2 by L2, right? Both K by L ratio and MRTS. So MRTS at point A is given by the slope of the isoquant at point A, and MRTS at point B is given by the slope of the isoquant at point B. MRTS will change, right? So the elasticity of substitution, which we denoted by this sigma, this is defined as the ratio of the proportional change of K by L to MRTS, right? So is defined as is sigma is defined to be the ratio of these proportional changes. To be the ratio of these proportional changes, right? So let me also write a formal definition so that you understand this. So for a production function, for a production function, Q is equal to f of KL, sigma measures the proportionate change in K by L relative to the proportionate change in MRTS. Relative to the proportionate change in MRTS. So basically you mean this. Proportionate change in K by L upon proportionate change in MRTS. So, of course, you can write proportionate change in K by L as K by L at point B minus K by L at point A upon K by L at point A upon MRTS at point B minus MRTS at point A upon MRTS at point A. So, this could be written also as del log of K by L upon del log of MRTS. Del log of K by L upon del log of MRTS. Right. I hope you know this. I mean, this is exactly like your elasticity. So I don't know whether you remember this or not. So if I have a function, let's say p is equal to f of x, right? So that's a demand function which I have. So I can actually write this also. So I mean, when I write the elasticity, how will I write? Del x by x, that is the proportional change in x, upon del p by p, that is the proportionate change in p. This could be written as del x by del p into p by x. That is what elasticity is. But I can also write this in terms of log. How? I can write this as log of p is equal to log of fx, or let me just write x, let's say, right? So if I take the total derivatives, d log p is equal to d log x, right? So what is d log p? Hmm? That is 1 upon p, that is the derivative of log p dp, is equal to 1 upon x, that is the derivative of log x into dx. Hmm? So dx by dp, you can just take it up like this, dx by dp into p by x. This is also, let's say, equal to whatever. And you could have also, so either you can write your elasticity in this, don't write 1, or you could have also written it like this, d log x upon d log. You can also write it like this. So this is also the meaning. This is also the same meaning. So otherwise, you can also write it like this: d log of, sorry, not d log of, dk by L upon dmrts into mrts upon k by L. You can also write it like this, right? You can also write it like this. Hmm. So we generally use this definition. It is easy. So I've just told you how why we are writing it in this fashion and not in any other fashion, right? So along an isoquant, when you are moving down from A to B, right, your K by L ratio is also falling. Here you're using more capital, less labor. Here you're using less capital, more labor. So K by L ratio is falling. And not only that, your slope is also becoming flatter. So slope of the isoquant at point A is this, which is steeper, and slope of the isoquant at point B is this, which is flatter. So slope is also getting flatter. So along one isoquant, along one isoquant, the MRTS will decrease as K by L ratio will fall. MRTS will also decrease as K by L ratios fall, right? So, I mean, you can just think of like this. So if MRTS is not at all changing with a change in K by L ratio, you will say that substitution is very easy. It is very easy to substitute, right? So you can just think of like this. If MRTS does not change at all, for changes in K by L, we might say substitution is easy, right? So the ratio of the marginal productivities is not at all changing as K by L is changing, right? As the input ratios are changing. So this generally happens in case of perfect substitutes, kind of the production function. Perfect substitutes kind of production function. What about the other one? So if MRTS changes frequently, or it changes very rapidly for even a very, very small change in the K by L ratio, then you say that substitution is very, very difficult, right? If MRTS changes rapidly for small changes in K by L, hmm, we would say substitution is difficult. We would say substitution is difficult. So a very small minor variation in the input productivities will bring about a huge change in MRTS, right? So this happens in case of perfect complement kind of production function, right? And this elasticity of substitution is a scale-free measure of how easy it is to substitute this, right? So this is a scale-free measure of responsiveness. scale free measure of responsiveness, right? So let me just, I mean, can we just give some points to it and make it more understandable? So let us say I have 5 labor here, 20 capital here, 10 labor here, and 10 capital here, right? Okay. So if I have this, then how do I get the, what is the K by L ratio at point K by L ratio at point A, it is 20 upon 5, 4. K by L ratio at point B is what? 10 upon 10, which is equal to 1. MRTS at point A is the slope of this line, right? At this particular point, that is just 20 upon 5, 4. And MRTS at point B, right? So only at this point, so you can just assume it to be 1, right? So elasticity of substitution would be what? The change in K by L upon this guy, your change in MRTS, proportionate change. So it is what? Change in this MRTS. So it is 1 minus 4. So this is K by L ratio at point B upon K by L ratio at point A upon 4 upon MRTS at point B minus MRTS at point A upon MRTS at point A. So this is what you get as 1. So this is what elasticity of substitution is. This is what elasticity of substitution is. So in a sense, I mean, basically, if you get the positive value of sigma, right, then you say that there's, yes, there is a certain degree of substitutability between the production inputs. A positive value of sigma indicates a certain degree of substitutability between production inputs. Between production inputs, right? Between production inputs. So if sigma is high, right, then MRTS will not change much relative to K by L, and isoquant will be relatively flat. So you can have a high sigma, or you can have a low sigma. So high sigma is this. So if sigma is high, MRTS is not going to change much, right? MRTS will not change much relative to K by L, right? And the isoquant will be relatively flat, and the isoquant will be relatively flat, right? So when there are, let's say, many people to run machines, I mean, when there are many people to run machines, uh, then you can actually introduce machines, right? While there are still enough people to run machines. Uh, when there are very few people, uh, then in which are involved in the production process, then it is difficult to swap machines for people. So there you will have low sigma, right? There you will have low sigma. So you can write it like this. So let me just define it in one way and then I'll come back to this particular point. And a low value of sigma would mean what? That you have a very curved isoquant. You have a very curved isoquant. So MRTS is going to change hugely by a very, very small changes in K by L. A low value of sigma indicates a rather curved isoquant. So a high value would indicate a relatively flat isoquant. Mhm. MRTS will change by the substantial amount as K by L changes, right? This I'm giving you a picture for the next class, right, where we will be talking about perfect substitutes, kind of elasticity of substitution. What happens to elasticity of substitution in a kinged isoquant, for example, min of AK comma BL. So those kinds of things. I just think about it. A high value, so it is harder. For example, there are in the production process you're using both machines and labor. So if there are very few people involved, it is difficult to swap machines for people. So low value of sigma. So you can just think of like this. It may be harder to swap machines for people. Means you cannot, I mean, substitutability is low, low sigma, right? When only a few people are involved in the production process. When only a few people are involved in the production process. Whereas it is easier that you can introduce machines if there are enough people involved in the production process. So means you're trying to substitute machines easily in place of people, whereas it is easier. Means your sigma is higher, whereas it is easier to introduce machines that is high sigma, while there are still enough people to run machines. While there are still enough people to run machines. You with me, beta? So, I mean, in this recording, what you've learned what do you mean by elasticity of substitution? Graphically, how do you think about it? And also, one more thing, in general, I mean, your sigma is going to change along an isoquant, right? So, sigma is going to be different at different points along an isoquant. Let me write that point also. Mm. So, in general, you can just write it somewhere. In general, sigma changes at different points along an isoquant. Sigma is going to change at different points along an isoquant, right? So what is it that you've learned? You've learned what is the meaning of elasticity of substitution. And although you have also a constant elasticity of substitution case, so but I'm just doing this simple case here. You understood what is the meaning of high sigma or a low sigma, although we have not seen the example yet. A very theoretical example I've given out here. What is the meaning of high and low sigma? And a very, very simple numerical here. And here I've just told you, I mean, what is the definition or what is the formula for elasticity of substitution, right? So what is the formula for elasticity of substitution? So this is what I wanted to do in this class. Thank you, Beta.